Hello, yeah. Okay, let's get restarted. Okay, remember, so I want to discuss two topics I told you yesterday. So the idea of yesterday's lecture was to play a bit with the particle physics. I will come back to the equation that we discussed just before, for instance, for WIMPs. So the n dt plus 3hn is equal to minus sigma v n square minus n equilibrium square. Yep. So remember that we say that this piece here on the left corresponds to the Liouville operator. So basically, and it's basically a total time derivative. So it tells me that the n, so the number density changes because the universe expands, right? N is the number density, is the number of dark matter particles over a volume. The universe is expanding, so that means that the density decreases just because the box is bigger, right? And h corresponds to Hubble, to have Hubble expansion rate. It measures how fast the universe is expanding. And for instance, in the exercise, we suppose that the universe was dominated by standard model radiation. That's an assumption. Okay, that's this term on the left. And this term of the right corresponds to the particle physics. So really your model. And this we saw different possibilities for this term on the left. This, for instance, corresponds to the annihilations. We said we could have co-annihilations, semi-annihilations, and then this term will be n squared minus n times n equilibrium. Or this 3 to 2, it was n cubed minus n cubed, n squared, n equilibrium. Yeah, different possibilities. Again, the point is that on the right-hand side corresponds to the collision operator, and it really depends on the particle physics, right? If dark matter, I mean, if it's annihilating, blah, blah, if it's decaying, if you have a WIMP, for instance, if you have supersymmetry, all that is encoded here in the thermally average annihilation cross-section. Yeah. And in particular, I think Graciela will focus on this part. Yeah. And that's also what we discussed yesterday. Today, instead, I want to discuss this piece here. Yeah. I want to discuss of the evolution of the universe, and this will be very general. So it will apply, for instance, to dark matter. But it will also apply to any other process that happened in the early universe. For instance, you want to compute baryogenesis via leptogenesis. Or any process that happened in the early universe. If you care about gravitational waves produced during inflation, you have to have all the cosmology under control, right? So the discussion at this the first half is completely general. Yes, so the idea to discuss today to try to understand what's the thermal or non-thermal evolution of the early universe. And when I say early universe, I mean before BBN. Remember, BBN is Big Bang nucleosynthesis, and Graciela already discussed a little bit about that. And it happens when the universe, early universe, when the temperature of the photons was in the MeV ballpark. Graciela say 5 MeVs, something like this. And it's interesting because we, at BBN, we have, the history of the universe from BBN on is kind of under control. We know that the moment of BBN, so when the temperature of the universe, of the photons, if you want, was smaller or the order, okay, say MeVs again. So this is BBN. We know that the universe was dominated, expansion was dominated by standard model radiation. So Hubble expansion dominated by standard model radiation. Yeah. And we used that in the previous exercise. So what we say is that H, remember I had a typo here, is standard model radiation over 3 m Planck square. Yeah. In general, here you have to put all the energy density and energy. So in general, you expect here, let me put it this way. And I have to make a sum here over all energy densities. This is the Friedman equation. Yeah. So Hubble expansion rate is the square root of the sum of all energy densities over 3 m Planck. And in particular here, what you expect to have is, for instance, the cosmological constant. You can have curvature k over a squared. So this is the curvature of the universe, plus non-relativistic particles, plus relativistic, plus blah, blah, everything. Yeah, the square root. In general, that's what you expect from the Friedman equation. However, in the early universe, cosmological constant is subdominant. Yeah, cosmological constant is only dominant at the very late stages of the universe, so we can forget this part. We know that the universe is basically flat, right? It's flat now, so at the early universe it was even flatter. So we can forget this part. And we also know that relativistic degrees of freedom dominate with respect to non-relativistic, because non-relativistic typically are Boltzmann suppressed, they are in equilibrium. So you expect non-relativistic to be subdominant, so get all relativistic particles, so radiation. So that's exactly what we did in the previous exercise. We assumed that this was dominated by standard model radiation. Yes. And we say that standard model radiation is basically pi squared over 30, this G star, and T power 4. That's the important thing. It's a power law. It goes like T power 4. Energy density, energy over a volume, energy power 4. So that's the first assumption. It's really an assumption. We don't, okay, no. After BBN, we know that this is the case. Number one. And number two, we also assume that the standard model entropy, capital S, okay, standard model entropy, which I call capital S, is conserved. Yeah. And also, this is what is called by Graciela. So standard model entropy is entropy density of times the volume, easy. And the volume is A cube. And standard model entropy is, we also had this expression before, standard model entropy density is 2 pi square over 45 G star S T cube. Yeah, we had these expressions of entropy density and energy density in the PDF. And this is interesting because if entropy is conserved, exactly we discussed that yesterday as well, that means that entropy density times A cube is conserved, is constant, and it automatically implies that the temperature goes like 1 over A. A is the scale factor of the universe. Yeah. So that means that the universe expands adiabatically. Adiabatically is here, adiabatically. We assume adiabatic process. So you have an expansion, adiabatical expansion. That means that the temperature decreases, the temperature of photons, let me emphasize this, decreases because the universe expands. Okay? And temperature goes like 1 over A, because everything is relativistic. So we know that these two conditions are fulfilled after BBN, right? What happened before BBN? What happened after BBN? We don't know. So the idea of standard cosmology is to do a shameless extrapolation. We say that what we know at the moment of BBN, so when the temperature is order of MEVs, we say that it will also apply for the early universe, where the temperatures were super high. What temperatures? I don't know what the highest temperatures of the universe, but it could be 10 to the 10 GVs or something like this, I don't know. But really what we're doing is an extrapolation. Extrapolation. Let me put it like this. But we really have no control, right? So we hope that this applies. However, there's really no control. So when we make the extrapolation of 13 order of magnitude, right? From 10 to the minus 3 GVs to 10 to the 10, I don't know. The highest temperature reached by the thermal bath, 10 to the 15 GVs, I don't know. So, so here in the standard cosmology, we have the word standard, right? So standard model for the cosmological model. And so this word standard is here, but it's also in the standard model of particle physics. And so the same word will have a complete different meaning. When we say standard model of particle physics, standard means that this model has been tested to death, right? So we are super sure that the validity of the standard model up to the TeV scale, whatever. But we are never doing an extrapolation. A standard model, okay, it works until the TeV scale. At 1 PV, we don't know. We are happy to accept that there are supersymmetric particles that have Kaluza-Klein, so infinite towers of particles per standard model particle, right? However, when I say standard cosmology, it's not that we know what happened after BBN, but really we're extrapolating. So just emphasizing this point, a shameless extrapolation at the highest temperature reached by the thermal bath. So what we're assuming is standard model entropy is conserved, so that temperature always scale like 1 over the scale factor. Hubble is dominated by standard model radiation, so that Hubble, that implies that Hubble goes like T squared over M Planck. And that's exactly what you use in the exercise, these two things, right? Hubble is square root, so T square root of this T squared over M Planck. Okay? Standard model, standard cosmology. And let me emphasize, I'm saying all this because in order to solve the Boltzmann equation, and you saw that, we're not really solving this because this is very difficult to compute. Why? Because this depends on time, but this guy, and this guy depends on temperature. So we have to know how one scale with the other. So even if it's like the Boltzmann equation that you can compute from first principles, this is not what you will solve. You have to go from this to the y over the x, blah, blah. You have to assume these two things. So the idea is to see what's the impact if you go to I mean, maybe more, I don't know if to say realistic or more general case where this uncertainty, we will to try to bracket this uncertainty. We will not focus on these two things. Okay, we will study these two things, but we will go beyond this approximation. See what happened if you assume, for instance, that not all the processes were adiabatic and that always the expansion rate was not dominated by standard model radiation. So the idea is to see what's the impact of non-standard cosmology, and what's a non-standard cosmology is any deviation from the standard cosmology, a surprise. So any deviation from these two assumptions. And it is not like crazy ideas. We know that there were, in the early universe, these two conditions were violated. We are sure that they were violated. For instance, in the case of reheating. So Graciela discussed about inflation, cosmological inflation. And remember, the idea of inflation is that the early universe, we had this epoch, very early universe of exponentially fast expansion. So the scale factor grows exponentially fast, right? So you have a number of particles in a box. The box expands super fast. So at the end, you have basically nothing, because the number density is super diluted. Even if the number of particles is not changing, the size of the box increases a lot. So the number density drops exponentially fast. So at the end of this expansion, exponentially fast expansion, at the end of inflation, you expect the universe to be basically empty with respect of maybe an initial population of standard model particles. So the universe is dominated not by standard model radiation, because it's subdominant because of this expansion, so we are violating this, but it will be dominated by the inflaton, right? The inflaton, the particle that was responsible for this exponentially fast inflation. So we know for sure that this condition was violated during, for instance, during inflation or even during reheating. And after this inflation epoch, we have to repopulate or to populate for the first time the universe with standard model particles, right? With photons, with electrons, with neutrinos. So the idea, so the common law is that this inflaton produces the standard model via decays, via annihilation, via non-perturbative processes. And therefore, if the inflaton is transferring energy to standard model, means that standard model entropy is violated. So it's a non-adiabatic process because you have a decay, right? Out of equilibrium decay of the inflaton or annihilation into standard model. So during reheating, this condition for sure was violated. Okay, so we are for sure in the early universe, the standard cosmology does not always apply. And this was a half-an-hour introduction. Okay, so I think I convinced you guys of the importance of these deviations from the common law of the standard cosmological scenario. So we'll study in particular very fast two options. One is the early matter domination. EMD. And the idea is very simple. The idea that we have an early matter domination. Good. Why is this natural? Remember, Hubble, for radiation, if you have relativistic particles, not Hubble, sorry, energy density of relativistic particles goes like 1/8⁴, 8 scale factor. And why is that? Because it's energy over a volume. So you expect to go 1 over the volume, so 1/8³, but energy redshift as well. So you have a redshift plus the expansion of the universe plus the volume. So that means that the energy density has to go always of radiation like 1/8⁴. Yes? And you can see, for instance, here, if this T to the 4 and T is 1/a, you recover 1 over scale factor 4. That's for relativistic particles. While for non-relativistic particles, this goes like 1 over the volume. Yes, because it's number of particles over the volume volume increases, so it's 1 over the volume. So there's no redshift. Energy has redshift, so it cools down faster. That means that you have, suppose you have the same number of relativistic and non-relativistic particles, right, in a volume, and it increases. So the two energy densities will go down, right? They are getting diluted. However, these guys are getting diluted faster because they redshift. So even if you start with the same population of relativistic and non-relativistic particles, these non-relativistic will eventually dominate. Or if you want, if you start with a universe which is full with relativistic particles and a very small amount of non-relativistic particles, even if the initial condition is that this is completely subdominant, eventually these guys could be the dominant, just because they get diluted less fast. So these get diluted very fast. So eventually, even if you start with a subdominant population of non-relativistic particles, this could dominate. And then you have a matter domination, so because it's non-relativistic matter, early universe. Yeah? So that's the idea. So here's the school of dark matter and neutrinos. So this come naturally if you have heavy particles. For instance, you can imagine right-handed neutrino that you need for baryogenesis via leptogenesis. So you can imagine that you have a guy, a right-hand neutrino with a typical mass for leptogenesis of 10 to the 10 or so, like these GeVs, with a lifetime, long lifetime, but long lifetime is like second, right? You wanted this guy to completely disappear or to be subdominant before the onset of BBN. And this is like TBBN is like 1 minute. Okay, say order minutes. Minutes, right? So if you have, for instance, a heavy right-hand neutrino with a lifetime of 1 second or few seconds, it's fine because it will completely disappear before the onset of BBN, so you will not mess up the BBN thing. However, this guy with a heavy guy with a long lifetime could eventually dominate the total energy density of the universe, right? So at some point, the expansion of the universe will be dominated by this heavy neutral guy, heavy right-hand neutrino. And it will decay, injecting entropy, and then breaking this naive expectation. So that's one motivation for early matter domination. We have also discussed about primordial black holes, and primordial black hole is also a source, a possible source of early matter domination. For instance, you can imagine that after inflation, you have this population of primordial black holes. I don't care how they were produced in the early universe, but you have them, right? You don't expect them to move at the speed of light, right? So you expect to be kind of at rest, to be non-relativistic. So you have a broad concentration of matter. It's not a particle, it's a macroscopic object. Non-relativistic, and they will eventually evaporate, Hawking evaporation. And if their mass is in the ballpark of grams, kilos, or tons, so very small primordial black holes, they will evaporate, Hawking evaporate before the onset of BBN. So you want them to be lighter than, say, few tons in order to fully evaporate before BBN. And these guys could also trigger an early matter domination era. Okay, so we are convinced that this could be interesting. So what I have to do is exactly the same exercise that I put in the PDF at the very end. So what you have to do is we have to keep track of the evolution of the energy density that is dominating the universe. So we assume that you have a heavy guy. So let's assume it's right-hand neutrino. For primordial black holes, it's exactly the same. I will tell you the details afterward. But let's assume that you have a guy phi, right? It's my right-hand neutrino, the heavy guy with a long lifetime. So you have to keep track of its energy density. Its energy density will be rho times rho phi, energy density of this guy. Yeah.
Sorry, Professor. I was just thinking, you are talking about the right-handed neutrino as a candidate of dark matter.
No.
It's just right-handed neutrino.
Yes, okay.
Okay.
No, just, yes, so because I want it to decay. So,
okay.
And it decay very fast, so it's not a viable dark matter candidate.
Yeah, it's because I remember that if you take the right-handed neutrino as a candidate of dark matter, the structure formation could be messed up because the structure will not form in top up. It's just in the opposite case. So
yes, that's true for the standard model neutrinos.
Yeah.
Yeah, right. I really want. I say right-handed neutrino, but in general, it could be any particle heavy and long-lived enough.
Okay.
So right-handed neutrino is a possibility, but in that case, it will not be a candidate for dark matter.
Okay.
In general, right-handed neutrinos could be candidates for dark matter, but if they are like in the KV ballpark.
Okay, but we are talking about that this particle will decay after the VVN because
before.
Before the VVN,
yes.
But if decays in the VVN, it cannot change the abundance.
Right, and that's exactly what you want to avoid. So you want to have an early matter-dominated era, but you want it to finish before the onset of BBN.
Okay.
Yeah.
Got it.
Yes, thank you. Yes. So, okay, I just say right-hand neutrino because it's like a natural candidate for this, but you can also, you have these moduli that come from supersymmetry, or these heavy guys that come from God theories. They could also be here. It is very general. You just want a guy a particle, for instance, but it could be a primordial black hole, right? So it doesn't have to be a particle that dominates the total energy of the universe. Basta. Yeah? So suppose this guy is phi. Why not? So right-hand neutrino moduli, yeah, got with an energy density rho phi. It's non-relativistic, so energy density is mass times number density. Yeah, I want to track the evolution of the energy density of this guy, right? So I will study the evolution of n because the energy density is just times the mass. And I know how to compute this number density because I just follow what the Boltzmann equation for dark matter. So phi dt, right, plus 3h and phi. Yes, and phi is not dark matter, but it's a number density of phi. So the guy triggering the early matter domination. So this, as I told you, this is a Liouville operator. It's completely universal. So exactly the same as there. The right-hand side is the collision. It will be different, the interaction case. So this guy, I'm assuming that it's decaying. So I assume that phi decays into 2 standard model particles. E plus, E minus, QQ bar, Higgs, whatever. Because they will thermalize. So minus, because it's decaying, in each decay we're losing these particles, right? So if this happens, I'm losing particles. So minus, gamma is the decay width of phi times n phi. I mean, the detail doesn't matter much. The idea is for you to understand the structure. So the evolution of these guys is due to the expansion of the universe. It's positive, but if put it here is negative. So the universe is expanding, number density is decreasing, so it has to be negative. So I put it positive here, but if you put it here, it's negative, right? On the right-hand side, it's negative. And it's proportional to h because it's Hubble expansion, 3 because it's this. So the universe has 3 dimensions of space. And also the changes because this guy is decaying, and gamma is the decay width that you can compute using the Feynman diagram, for instance. Gamma is the total decay width. So imagine in terms of Feynman diagram that you have whatever, this process like this, phi decaying into whatever, into Higgs, I don't know, anything. So you have your Feynman diagram. You can compute this decay width, right? So you have the amplitude. You make the integration of the phase space, blah blah. So you compute the decay width, and that's it. Yes, so gamma is the total decay width, and you can associate to the decay width the typical lifetime of phi, which is basically 1 over gamma. So I want gamma phi. I want this to be smaller than, say, 1 second, because I want it to decay before the onset of BBN. Okay, phi is decaying, and is decaying to what? Into standard model particles. So I can also track the evolution of the energy density in the standard model, so in radiation, I mean in the standard model radiation over dt, plus, okay, the universe expands, it will get diluted, so it's a negative, but they put it on the left, it's positive. 4h rho radiation, sorry. And why 4? Because it's non-relativistic is relativistic particles. So we have the expansion, the increase of the volume, but also the redshift. So this 4 is very important. And I'm getting particles, standard model particles, because of this decay. So each decay, I lose phi, but I win standard model particles. So here I have a plus, right? It's the same term, right? So it's the conservation of energy. So phi and m phi. It's basically the same thing, right? So the energy density that I'm lose from here, I'm transferring from here to here. Here is number density, here is energy density, so I have to put an m. But it's basically the same term, here and here, minus and plus. And these two equations, you can find it in the PDF that we discussed. So I also encourage you to solve this equation. And you know, these equations are very nice to understand, but they're completely useless because the same thing, right? So this depends on time, but it's on temperature, so you have to make a change of variable, blah, blah, blah. But it's exactly the same idea, right? So these two equations are these, and this one are completely different. However, they're basically the same, right? So these two equations are coupled because of the source. So this guy is injecting entropy here. So it's transfer energy from phi to standard model. So these are coupled because of the source term, but also because of Hubble. So Hubble, remember, is 3m Planck square rho radiation plus rho of phi, and rho phi is m phi and phi.
Professor, again.
Yes.
Just I was idea, but because I don't know if it is possible, but we can, for example, motivate a particle that it can decay during the, for example, the formation of the lithium-7. And as we know, we have a problem with that. Maybe if decay in that time or something, it can destroy the element. And I don't know, maybe if it can be.
Yes, right. So I'm not sure I mean, what you say, I think is controversial, if there's a really lithium problem with lithium-7 or not.
Yeah.
But yeah, so I'm being very maybe conservative. I don't want to touch BBN.
Okay, okay.
But of course, you can do that. You can make this decay during BBN, and you will have some modification of the naive expectations. And of course,
But
the abundance of lithium and all the other abundance
but of course,
will change.
respecting, we just conserve the, for example, the helium or the other elements, but as we know, the difference between the observed the theory is with the lithium. But this is possible to apply in some model or something that we can do that.
Yeah, but the problem is
naturally?
that here you're injecting entropy in the standard model. You're heating up a little bit the standard model. So you will mess up with not only with lithium, but everything.
But
So you have to be very careful. But of
So-
course, you can do that. Yeah.
okay, but in this case we have to work with non-standard cosmology, I think.
Yeah,
Not
that's what
with
we're
this
doing.
one.
That's
Okay.
non-standard cosmology.
Okay.
And why? Because we are violating these two assumptions.
Okay.
Assumptions.
Okay, thank you.
Yeah. Okay, yes, so I'm saying that these two equations, these for the background, are coupled because of the source term, but also because of Hubble. So H, that enters here and here. Yes. Right. Yes, good. Suppose I don't have the particles are stable. I don't have a collision term. So I put these two terms on the right to 0. Yes, suppose you have that. So the standard model and phi are completely decoupled. Yeah. If I put these two terms to 0, I will do it for you. Easy. 0 and 0. If you solve these equations, this equation will tell me this, and this equation implies this. So these 3 and these 4 mean that if there are no interactions, so if these terms are 0, they're giving how the energy density have to scale. So non-relativistic have to scale like 1 over the volume, because number of particles over the volume, right? However, for relativistic particles, energy density is energy over the volume. The volume is like a cube, and the energy has the redshift. So it's an extra power of a. So instead of a cube, you have a power 4. So you can do this exercise. So you can compute these two things and see how radiation and energy density of non-relativistic particles like this scale. So basically, these 3 and these 4 are these, 4 and 3. Yeah?
Nicolás.
Yes. Yeah.
Sí, are we still working for a possible heavy neutrino as the phi particle?
Could be. It's completely independent. But yeah, could be.
What about the lepton number conservation in that diagram? And maybe like the dimensions it would have in a Lagrangian?
Okay, let me, okay. Yes. in that case, if it's a heavy neutrino, I can have n right-handed neutrino decaying to a neutrino and a Higgs.
Yeah.
So
Yeah.
you have conservation of lepton number, is dimension 4, that's fine.
Okay.
But here, at the end, here is the same. Okay. For me, this diagram and this that I wrote before, okay, and exactly the same as before. Phi into standard model. These are the same, right? Because neutrino and Higgs are standard model particles. So, and they will thermalize. So they will all create this thermal bath.
Yeah.
So if I put here neutrino, Higgs on 2 quarks, on 2 W, whatever, it's fine. It's at the end, it's exactly the same.
I understand.
Yes.
Thank you.
Thanks. Yeah, I'm super late. Okay. So this is the evolution of the background. So this will give rise to a non-standard evolution of the universe. And the idea of the last point of the exercise was to solve this numerically. And if you do that, you will get something like this. So I give you the exercise and the answer. Perfect, right? And from this, actually, so it's the plot on the left. And I will guide you to understand it. And on the right, I'm plotting the temperature. How can I extract the temperature? It's easy. Because if I solve this equation, I will know the number density of phi and the energy density of radiation of the standard model. But I know that the standard model radiation, I mean, this equation will always apply. So if I know what's the energy density in radiation, I will know the temperature. Yes? So there's a one-to-one correspondence between energy density in radiation, standard model radiation, and the temperature. So the idea of the exercise was to solve numerically these two things. Again, make the change a variable, solve numerically, and then you will get exactly, hopefully, the plot on the left. And for the one on the right, you just take this, use this expression, and extract the temperature. That was the first part. And once you have that, so you have the evolution of the background, you can use another equation, 1, 2, and use this one, third. So solve 3 coupled Boltzmann equations and see what happened with WIMPs, or so annihilation, semi-annihilation, FIMPs, no, this what? SIMPs, sorry, WIMPs, blah, 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 blah. So all that I told you yesterday, and basically all that Graciela will tell you can be redone in the case of non-standard cosmology, and in particular during early matter domination. And again, early matter domination could be triggered by a heavy right-hand neutrino, by a primordial black. Okay, case of primordial black hole. I mentioned primordial black holes. So you can do exactly the same. So it will not be phi, but you will put here PBH. So that's the main difference. PBH, PBH, blah, 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 PBH, 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 and PBH. And that's it. The difference, let me put it, PBH, okay, I'm tired, is that this guy will change. So remember I told you that this corresponds to the decay width, total decay width, that you can compute using your Feynman diagrams. However, you cannot do the same for a primordial black hole. It's not really decaying, it's Hawking evaporating. You can compute this, of course, it will be a pain in the neck to compute. The main difference is that the primordial black hole is evaporating. That means that its mass is changing, right? Its mass is decreasing. Therefore, if you want, you cannot use this exactly as it is, because in the case of an early matter domination, a decay, this guy is a number. However, in the case of primordial black holes, if you want, it will be a function that depends on the mass that varies. So it's like a little bit more complicated, but the general picture is the same, right? So it's not, you can think this as a particle, a primordial black hole, so first approximation as a particle that decays with a time-dependent decay width. So with a gamma, which is not a number, but it's a function of time, or if you want, of the temperature, blah, 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 yeah? So, and I'm running out of time. Okay, I want to discuss this plot. So this plot is a bit difficult because I did it changing the number of degrees of freedom. Remember the G star and G star S, the number of degrees of freedom that enters in the energy density and entropy density. So they're like wiggles, but let me draw it here. So it's a plot as a function of the scale factor A of energy densities. But I know that energy density scale either like 1 over A cubed or A squared. So let me multiply this by A power 4 times A power 4. That means that free radiation will be flat, right? And matter, so non-relativistic particle, will increase linearly with A, because it's 1 over A cubed times A4, linear with A. So this will something like this, and at some point it decays. This will be energy density of phi. Yes? Multiply times A cubed goes linear with A, and at some point it decays, right? Completely disappear. And now I have, let me put some scales here. So this scale, what I call A end, it means the moment when it completely decays, something like this and like this. I will call a critical and a what? The equality. I need another color, blue. So that's for the energy density of phi. Now, ¿cómo es? Así. Something like this. The same color, no? Something like this. This is energy density of radiation times A power 4. So that's basically the plot of the left. So there's a period here where the energy density is dominated by phi. This is phi is dominant, right? So this is what I call early matter domination. So Hubble is dominated by phi and not by R. In this region here, I can feel that phi is decaying, is injecting entropy, and therefore I have a source. It's not free radiation, but source. So in this term, is non-adiabatic. And why is not adiabatic? Because in this region here, between these two lines, I can feel that the energy density is not scaling as free radiation, but they have a source term. And what's the source term? Is the decay of phi, right? Phi is injecting entropy in standard model. It's producing standard model. And here is an adiabatic. Adiabatic. Why adiabatic? Because I'm not feeling the decay of phi. Here in this part is radiation domination. Here in this part is radiation domination. So this is basically a sketch of the solution of this equation. So we see an era where you have early matter domination, where the expansion of the universe is dominated by phi. So I'm violating this equation, this condition, this assumption better. And in this era here, I feel the entropy injection. Entropy, they have a non-adiabatic. Standard model entropy is not conserved, and they have a violation of this assumption, right? So this is basically the plot on the left, and the plot of the right is basically the same thing as a function of the scale factor, the temperature, times A. I will expect T times A to be constant, right? Let me put again these 3 lines. So first, I feel that this is constant, right? Here is constant as well, but at some point, it goes up. And why is going up? Because I have a source. It's not free radiation. I have a source term, and therefore I have an increase of or a temperature that goes that is getting diluted, is decreasing less fast as free radiation. This early matter domination could be triggered by a heavy particle, right, a neutrino, by a primordial black hole, for instance. And okay, so you have the evolution of the background, and here, as I told you, you can solve the equation of WIMPs. And this was the last part of the exercise. So easy, no? And why it makes sense? Because if you want, okay, and the evolution, okay, remember that was the evolution of WIMPs. And now what happens if WIMPs are produced in this kind of backgrounds? So this is the evolution of WIMPs in the case of standard cosmology. And if I go to a non-standard cosmology, so an early matter domination, I will have these solutions. So they're very similar. At first approximation are very similar. So I have three plots here. Again, it's y as a function of x. And it's the same. So the blue, gray, whatever, is the equilibrium. The black is the solution, the numerical solution. And the first plot on the left, top left, corresponds to a freeze out that happened here in this area. That let's call it 1. So the freeze out is when the universe is dominated by radiation, right? So you have basically the same decoupling. So that matter is track in equilibrium, and at some point you have a decoupling, and it's completely flat. But at some point you feel the entropy injection, this non-adiabatic period, and therefore what you have is a dilution. And why you have a dilution? Because remember that what we want to fit is the dark matter number density. That's what we know. We know that this guy is energy density of dark matter over energy density of standard model. And this is basically 25% total, not standard model, total. Remember the 25%? So we are not changing the dark matter density, we are increasing this. Yeah? So we are diluting the dark matter, and therefore it goes down, right? So we are injecting entropy, we're creating more photons, more standard model particles, and we have a dilution in this area between these two lines when you have between what they call critical and end, which is exactly the non-adiabatic period where the guy phi is injecting entropy and getting diluted. So this is the first scenario, if freeze out happens here, but freeze out can also happen here. So let's call the case number 2 is this one here. So the decoupling is slightly different because it's decoupled when the universe is dominated by phi, so by this this early matter domination. So the coupling is slightly different, and then you have again the dilution. Yeah, that's the case number 2. And the case number 3, surprise, surprise, is this one when you have, everything. So you have a non-adiabatic phase, but and the universe is dominated by phi, and it's this case here. So you have a decoupling here, the freeze out. However, at the moment of the freeze out, you're not having a plateau, like in this case or in this case, but you have a dilution. Just after the freeze out, you have a dilution, the same dilution because of entropy injection. So it's again, for this exactly WIMP, so we're not playing with an exotic mechanism of producing dark matter, we're just playing with cosmology. Yeah, in particular with early matter domination. And you can do this. You have all the tools to exactly compute these plots. And that's the final part of the exercise. To repeat exactly this exercise, find the evolution of the temperature and the energy densities, and then compute the evolution of the dark matter, right? So solve this set of 3 coupled Boltzmann equations. Okay? And so Javier will tell you about this in his poster. So this is exactly the same model I presented yesterday. So it's a Higgs portal. So a singlet scalar that's coupled to the Higgs with the standard model. So this is a portal between the two sectors as a function of the dark matter mass. So we saw this plot exactly yesterday, so it corresponds to WIMPs. So order one couplings. So 1, 10 to the minus 1, 10 to the minus 2, and masses in the GV to TV ballpark. So 10 to the 3, 10 to the 6 GVs. 10 to the 0, 10 to the 3 GVs. This corresponds to WIMPs, and this corresponds to FIMs. So, and I think Graciela will discuss about FIMs, in non-standard cosmology. So in non-standard cosmology, in standard cosmology, you have this and this, right? But now what happens if you repeat the same exercise, assuming this is what? Exactly, early matter domination. You have that, so let me say a couple of things more. So this region here is excluded because I'm overproducing dark matter. So I have too much dark matter here between the two lines, while upstairs here and downstairs here, I have an underproduction, not enough. So if I allow the universe to have a non-standard cosmological era, in particular an early matter domination, I can populate all this region between the two lines, right? So all this parameter space is allowed, just playing with cosmology for exactly the same WIMPs, super simple particle physics model, but just playing with the early matter domination. So I can go from WIMPs to FIMs with early matter domination for different values of Tn, so the moment where early matter domination stops and when it starts. And all the details of how to do this and how we can test these scenarios we'll be discussing with Javier in his poster. So please go and ask him. And I have like a couple of minutes. Okay, questions or comments before that? Good. So I discussed early matter domination. I will discuss another scenario, and it's super simple. So a couple of minutes is more than enough. It will correspond to the case of low temperature reheating. And this seems like a super complicated thing, but and it is actually, you're right. However, there are cases where it's very simple. Because remember, after all, we say that during inflation, the energy density is dominated by this guy, by this inflaton. And during reheating, the reheating is there when this energy is transmitted from the inflaton to the standard model. So if you assume that during reheating, the inflaton has a mass, right? And it's non-relativistic, you will get back exactly to the same picture, right? So you just have to change PBH by phi, and phi will be the inflaton field. So you remove this, you put phi, n of phi, and phi now it's not a right-hand neutrino, it's really the inflaton. So not early matter domination, but let me. Now, it's not early matter domination, but it's reheating. And in particular, low temperature reheating. And now this guy, phi, is the inflaton. Yes. Low?
Low?
No, I mean, yeah, of course, yes. Low with respect to what? It has a dimension. Low with respect to something. So it has to be higher than the MEV. The same argument. You don't want to mess up with your lithium-7. But it's low, of course, it's not well defined. But the thing is that typically the common law is that if you have a Starobinsky inflation or alpha attractors, you expect the reheating temperature, so the end of reheating to be at 10 to the 10 or so. But there's no reason why it has to be that number or even that ballpark. But it's just a sociological problem. So people, I mean, the common law is that reheating happens at a very high temperature. So if you have a smaller temperature, smaller than, I don't know what, is low reheating temperature. So basically the idea is that if the reheating temperature is smaller or of the order of the typical scales of your problem. In particular, here we have the freeze out. So if the freeze out can happen during reheating, you will call it low temperature reheating. But I agree that it's completely ill-defined quantity. So small is, if you care about reheating in the process, it's low temperature reheating. But yes, it will be TV, 10, even 10 to the 9 or 10 to the 10 could be low temperature reheating. Yes, with respect to the temperature of your problem. So two more minutes, sorry. So it's exactly the same. So conceptually, it's completely different, but technically, again, it's exactly the same thing. You just change PBH by phi, and you say phi is the inflaton, and basta, right? There's one particular thing here, it's the initial condition. So you assume that after inflation, there's no particle, no standard model particles. So here in this case, you typically assume that the energy density of phi, or if you want here, the number density of phi at the initial condition, whatever it is, so A initial is equal to 0. So again, in the technical perspective, this is an initial condition that you have to set, but that's exactly the same set of Boltzmann equation, and therefore the solution is basically the same. It's basically the same. You had this, but I say that you have like 1, 2, 3, so you remove 1, 2, and that's it. Yeah? Because this is radiation, yes, sorry. Thanks, of course. Good. Javier, good. Yes, and exactly this equation. So this plot here is, no, wait. Yes, okay, it's that I'm not multiplying by 8 to the 4. But it's basically the same during inflation. So the blue line on the left is the energy density during inflation. During heating starts to decay, and it decays injecting entropy in the standard model. So you start here from zero. From 0, you start to create the standard model. So very fast it goes up, then it goes down, and but it's getting populated because of the decay of the inflaton in blue, and therefore the inflaton decays completely, and you have a radiation-dominated phase, and you have the equivalent of the temperature, and you can do exactly the same exercise as I showed you before. So it's exactly the same model. I'm not playing with the particle physics, but just playing with the cosmology, with that low temperature reheating. And here I say 10 to the 12 GeVs. It's called, for me, low temperature reheating, which of course makes no sense, but it's low with respect to the scale of the temperature of the problem, in particular the temperature of reheating. Yes, so again, the same thing. You have here WIMPs that will be discussed maybe tomorrow by Graciela. WIMPs here that in the standard model, in standard cosmology are two separated, disconnected solutions. But in the case of low temperature reheating, you can naturally go from one to the other, just playing with the reheating temperature, right? And again, all this parameter space that was completely excluded because have an overproduction of dark matter becomes viable. So I think that was basically what I want. Okay, and how to test it, you will ask here. Javier will tell you. This I have basically no time. But okay, so long story short, you have, if you want to have control of the dark matter, if your idea is to compute dark matter in the early universe, you have to be careful about the particle physics, see what are the mechanisms, if it's WIMP, if it's an ALP, and QCD axion, cannibal, all these mechanisms. Of course, you have to do that, but you also have to have cosmology under control. So it's a beautiful example. You have this constructive interaction between hardcore particle physics and hardcore cosmologists, right? And also see that the prediction, if you project the expectation in a typical particle physics plot, right? So couplings as a function of the mass. I mean, this goes like big chunk of the parameter space that you originally thought that were completely ruled out becomes viable. So this is good and bad. Good because you have a lot of freedom, but bad because we hate freedom, right? That's why I'm in the Emirates, but I cannot say that. Is that, I mean, the parameter space becomes super big, right? So you have like infinitely, even for a super simple dark matter model, you have that the parameter space becomes super large. Basically, everything is or could be compatible with observations. Okay, and I'm running out of time, so thank you very much.
Okay, so now we go directly to the question session. So you can ask any question to Nicolás, you can question to Pedro. And if you have questions to Graciela, unfortunately, she had to leave, but you can still ask the questions, and Nicolás and myself will try to answer the questions. If you ask something about double this dark matter, I would just say I don't know. But otherwise, if we know, we can answer. So ask the questions from the morning and from now.